Now going back to the partial derivative of the weighted input at some arbitrary neuron I, we already computed an expression for the partial derivative of the weighted input at neuron V here, which was the activation at neuron U from the previous layer. So let's just write that down. We're just substituting this expression with what we got here. So this was AU L minus 1, and this was when I is equal to V and 0 otherwise. Now going back to our outermost derivative, the partial derivative of C with respect to the weight, we got this expression previously, and then we looked for an expression for the partial derivative of the weighted input at some arbitrary neuron I, which we computed here. So we see that when our summation index is equal to V, we get a non-zero term, and when it's not equal to V, we get 0, which means that if we substitute this partial derivative here, we get a 0 term when I is not equal to V, and when I is equal to V, we get the partial derivative of C with respect to A, V, L, because I being equal to V means we substitute V as a subscript here, multiplied by the derivative of the activation at the VF neuron with respect to the weighted input at the VF neuron, multiplied by this expression, which is the activation of the UF neuron at the previous layer. So we've now completed the first part of step 1 in our derivation strategy, which is to find a generic expression for the partial derivative of the cost function with respect to some arbitrary weight going to a neuron in our output layer, which is this. Now our next step will be to consider the partial derivative of the cost function with respect to some weight going to layer L minus 1.